All right, let's go over our warm-up. I'm going to break this down into a few parts. This first one's going to be our free responses, and then a couple of things that go along with that. So, on this first problem, on part A, it actually was just a basic, simple question that identifying the probability of being unhealthy. What portion of the sample are unhealthy? So that was just these 4 out of those 23 that were unhealthy. So 17.39% of the sample was unhealthy. Then it asks you to make a 95% confidence interval for the average lead level of the crows in that region. So you want to define your parameter. Mu equals the average lead level of all such crows in the region. All right, then we're doing the conditions for one sample. This is a one sample T interval for means. So we had stated that this was a random sample of 23 crows from the region. Independent, 23 is less than 10% of all such crows from the region. And large enough? No. The 23 is not greater than or equal to 30. So we would have to do a dot plot or a histogram. However, this stem plot was given to you. So if you turn your head sideways and you look at this, you can then see, that we've got this shape that is somewhat symmetric and unimodal. See here, we've got this shape that's somewhat symmetric and unimodal and has no outliers. So we just state that it was sun, and so the approximately normal model applies. All right. So this is called a one sample T interval for means. Now, technically, you can do the just T test in your calculator, or T interval in your calculator. Okay? So, technically you can do that. I want you to, because I'm just a meanie, do these one sample problems by hand. So this interval, here's how you do that. We were told that the sample mean was 4.9 parts per million and a standard deviation of 1.12 parts per million. So remember how to make an interval. It's your statistic plus or minus your critical value, that's based off of the confidence level times the standard error of your statistic, which is this S of x over the square root of n. So this x bar, that's your sample mean of 4.9 plus or minus T star, critical value based on how confident we are going to be, which they tell us to be 95% confident. So I'm going to come down here, inverse T with, if I have 95% in the middle, I have 0.025 in the tails, and I have 22 degrees of freedom. That gives me negative 2.07, so I know that critical value is 2.07. And then here is that standard error of the x bars. So there is my 4.9 plus or minus 0.48. So the interval is from 4.42 to 5.38 with 22 degrees of freedom. So I'm 95% confident that the true average lead level of all such crows in the region is between 4.42 parts per million and 5.38. Now, look and answer the question. The question is, I don't know if they had a question. Okay, so they didn't really have another separate question. If they had, you'd want to make sure you answered that. It doesn't look like they asked this. Now, let's talk about how would you have done this problem by hand if it was a one sample T test. Okay, so in order to be a T test, they would have hypothesized a claim. So let's suppose that they hypothesized that the average lead level was 4.5, or that was the current rate, but you suspect it's higher or whatever. Okay, so you suspect it's higher. So to find that p-value by hand, you have to get your t-score. So that's your x bar, okay, minus that hypothesized value over that standard deviation of the statistic. That's this here. Okay? And so there's my t-score. So if you were to look at a picture, here's what you have. If the mean is 4.5, then all the samples should be centered around 4.5. But you got this sample here. So we need to find that p-value. And so it is located 1.74 standard deviations above the mean. And so I TCDF from 1.74 to 99 with 22 degrees of freedom to get that p-value. So that means there's a 4.79% chance of getting this sample or something more extreme if the samples are really centered around 4.5. So if the null is true. And so that's pretty close to your 5%. So it's evidence to reject the null. We would end up doing that if we think it's higher. Okay, moving on. So here's 22. Here this is an interesting problem in 2014 on the AP test. They gave us information to carry out two independent samples t-test, but they also gave us information to be a matched pairs t-test. And this was supposed to be matched pairs. So they presented you with all the information and you had to decide which way to go. So because we were wondering if there is significant or if there's convincing evidence that on average women pay more than the men, but they were paired by the type of car, the car model, okay, which makes sense since we're comparing the women versus the men. So here's our test. So look at how this parameter is written. Mu with the W minus min, because they told me that's how they did this subtracting. The average difference in money paid for the same car in this county, women minus men. Define the way you subtract. All right, so the null hypothesis would say no difference. The women and men are paying the same amount on average. But then they wondered if the women pay more. Do the women pay more? So that's why my alternative had this greater than sign. All right, so my conditions should be for one sample of differences. My conditions should be for this one list of differences, okay? And furthermore, the picture that need to draw is this one here, not the one for two separate means. Okay, so again, you see how they gave you the information for the two separate means, even though you were supposed to use the one. So here we go. It was stated 8 randomly selected women-men pairs for the 8 identically equipped cars. So our independent 8 was less than 10% of all such car. And don't forget this, each woman-man car sale are independent of the others. So that is telling me this has no effect on this matched pair and has no effect on that matched pair and so on. Okay, so they are independent of each other. So now, it was not large enough, absolutely not large enough. There's only 8 or however many pieces of data, 8. But the dot plot above for the differences in the purchase price shows for women minus men, somewhat symmetric, unimodal, and no outliers. Is that really that way? I don't know, but I'm going to go state that and move on. So I'm going to assume the approximately normal model applies. Okay, here's the name. Matched pairs t-test for means. Now, you do not have to put this calculator stuff down, but here's what I went and did. I went and did a t-test in my calculator. So notice that the null hypothesis is a difference of 0. They gave me this information right here for the differences. That was this, I went ahead and put the summary statistics in instead of all of the individual pieces of data. You could have done all the individual pieces of data, but because I had the summary statistics, that's easier. So I put the summary statistics in the calculator. And then my tail, my alternative hypothesis, was a greater than. All right, so when I calculate, it gives me this, the t-score of 3.12. P-value. You must write the word p-value. Do not write p equals, because what is p equal? A proportion. Okay, and do not forget the degrees of freedom. They don't tell you that, but because it's a t-test and it was one sample, then it's in -1. Okay, so our p-value of 0.008 was less than alpha, so we reject HO, and then here is the conclusion. Since that p-value is less than alpha, I reject HO. There is evidence that, on average, women pay more than men in this county for the same model car. You could also say that there is a difference in the average price paid. So that kind of could have been said as well. Just make sure that you do not state this with two different averages. For example, it would be wrong to say the average for the women is more than the average for the men. That would be wrong because that sounds like two separate independent averages. All right, so there's the end of that one. And then here is one that ended up being two independent means. It was group A were the men on the placebo, and group B were the men on the cholesterol drugs. They were two separate sets of men. So I said mu of A is the average cholesterol reduction for all such men on the placebo, and I defined pre minus post because they actually did. It was interesting. It was two different sets of matched pairs. Okay, so it was interesting to see what that average cholesterol reduction was. Mu of B is the average cholesterol reduction for all such patients on the cholesterol drug. Now, our null hypothesis is that the cholesterol reduction is the same for the placebo and the cholesterol drug, but alternatively, we think that the cholesterol drug has a higher reduction. They set up in the problem, is it more effective? I think is what the way they worded it. Does this indicate that the cholesterol drug is effective, so more effective than exercise and diet alone? So that's a higher reduction. So that means that this mu of B is greater than this mu of A. And so that's going to play into how you put things into your calculator. If you put the placebo in first, which is natural to do, and you put the cholesterol drug in second, then you need to make sure that this is the highlighted alternative. Mu1 is less than mu2. Okay, that's the catch there. All right, so let's look at how we did the conditions. So I thought it was interesting that they said that these were 20 randomly selected men from the hospital. So that was interesting because that plays into who you can generalize to. So, but truly what was actually more important was this, that it was stated that we had 10 men randomly assigned to the placebo and 10 men randomly assigned to the cholesterol drug. So those were actually the two important statements to say about the randomness. Independent, so of course 10 is less than 10% of all such men on the placebo, and 10 is less than 10% of all such men that can be on the cholesterol drug, and assume that the men in each of these treatment groups are independent of each other. All right, so then here we have this large enough. They were not. So we had to do, since it's two independent means, we had to do two separate pictures. Okay, so this was a notice how I labeled this. Reduction for the men on placebo and the reduction for the men on the cholesterol drug. Okay, are they beautiful? I don't know about that. I mean, is this one on the left skewed to the right. I don't know. Assume. So that's why I put this word in here. I was uncomfortable saying, yes, they are definitely sun. So I kind of said, I'm just going to assume that both are somewhat symmetric, unimodal, no outliers, so the approximately normal model applies. All right, so I talked a little bit about this. You went and put this into your calculator as a 2-sample t-test, and I put the summary statistics in. And I talked about how I put the placebo in first and the cholesterol drug in second with this particular tail right here. So my t-score was negative 1.62, p-value 0.062, which the degrees of freedom also don't leave that off. They stated the degrees of freedom were 17.3. All right, so because that p-value is greater than alpha, I failed to reject. Okay, and in medical trials, they typically have a strong or a very small alpha. Okay, because they don't want to be just willy-nilly giving out drugs if they're not going to really have strong efficacy. So this was a low p-value, and that's common. So anyway, we failed to reject. So we do not have statistical evidence that the average reduction in the cholesterol. See, notice how I have two different averages listed. The average reduction on the cholesterol is more than the average reduction in cholesterol with diet and exercise alone. So I stated those two averages separately and that there's not evidence that one is more or less than the better reduction than the other. Lots of details on there. Okay, lots of details. All right, so there is your free response. Now, one quick word to mention, and I wanted to show you this. What happens if you are not given summary statistics? And you need to find that X bar and that S of X. Then don't forget, you can go to Stat Edit and put your data in the list, and then Stat over to Calc and do one variable stats. That will give you a printout with your X bar and your S of X. So I wanted to remind you of one other thing. Let's talk different standard deviations. The standard deviation of the population would be the sigma of X. And then you have one sample here from that population. That standard deviation is S of X. Okay? But this blue picture down here is a whole bunch of X bars. This is a sampling distribution of sample means. Oh, this was supposed to have a bar right here. So that is S of X bar, and that comes from this S of X right here divided by the square root of your sample size. Okay? So there is 3 different standard deviations for those 3 different distributions. All right. So that's the end of the free response. Lots of information there. And the next video will be the multiple choice portion of this.